Welcome to the AI Energy and Climate Podcast, a special series from the DSR Network hosted by David Sandalow.
Jensen Huang, welcome to the AI Energy and Climate Podcast. Thanks for joining us.
It's great to be with you. Thank you.
Well, we're honored to have you, and I'm looking forward to discussing a range of topics, including the potential benefits of AI, power demand for AI, your plans at NVIDIA, and more. And maybe let's start with the potential benefits of AI. What do you see as some of the most important ways that artificial intelligence can contribute to solving energy and climate change problems?
Well, artificial intelligence has the ability to understand data, understand, if you will, information at a scale no humans can. And you can understand, it can understand multimodal information from temperature to wind speed to, pressure, all at the same time. And it could study information across a very large scale, very large longitudinal scale. And so the ability to understand information and then be able to predict the future is quite an extraordinary thing. But let me take a step back and say something about how we got here. I think as you know, we invented a new way of doing computing called accelerated computing, and we reduced the amount of energy required to do computation. In order to increase performance, the fundamental way of increasing performance is to reduce computational energy, because whatever energy you use, or whatever energy you have, you have plenty of transistors to go over time to go and consume that energy. And so the less energy you use, the more computation performance you get. And so we introduced accelerated computing about 25, 30 years ago and really took a giant leap in the amount of performance or a reduction in energy that we were able to produce. And to the point where this new way of doing computation, new way of doing computing called machine learning, and just let the computer go study the data, was made possible. And so at the background, what really enabled it is accelerated computing and driving energy consumption down. And now we have this new way of doing AI. And of course, a lot of the conversation we're going to have is that there's two phases, if you will, of AI. There's the learning phase. We call it the training phase, training the model. And then there's the inferencing model, which is the application phase. It's a little bit like humans. We have to go spend 20, 30 years pre-training, going to school, and then afterwards we get to go apply it and inference, do the inferencing part of it. And so the training part of it requires a lot of energy. And but the good news is that most of the world's computation is really going to be about inference. And when you train a model to do certain things, the inference energy is incredibly low. And so we'll be able to talk about that during this talk.
It's interesting. Your comments about driving energy consumption down are counter to most of the narrative that we hear these days.
Yeah.
All this attention about how AI is driving up energy demand, and power demand. Could you say a word about what you mean about how AI is driving energy consumption down?
Yeah. You have to look at AI in its entire longitudinal aspect, because the goal of AI is not to train the model. And these data centers that we use to train a model are quite large. And you apply basically three things. You have to invent a model, and that model has to have the ability to learn the predictive features from the data that you're presenting. And so it could be a lot of videos, or it could be large amounts of telemetry data that's taken, about weather or the climate. It could be a whole bunch of words that you want to learn something about the language. And so you collect an enormous amount of data, and you have a model that you have to train, and it takes the computation, takes a computer to iteratively figure out how to predict, understand the features and how to predict the outcome. And so that takes a large computer to do. But the goal, of course, is not just to train a model. The goal is to use the model. Now, once you train a large model and the model is quite large. It's trillions of parameters large. But then what you do is you've now created, if you will, a professor model. You take this professor model and you distill it down into a whole bunch of little student models. And so the actual model that you use is not that big. It could fit in a cell phone. It could fit in a PC. It could fit in a self-driving car, for example, just one chip on a self-driving car. And the response time is really good. It's really fast. Just as, when we're using ChatGPT or Gemini, the response time is super fast. And because the model it's trained in a very large model, but it distilled it into smaller, medium, small, tiny models. Now, of course, these tiny models have the skills of the large model, but not the generalization capability of the large models. And so it tends to be a little bit more brittle, it tends to be more specific, but it has the capabilities to perform whatever task that it was fine-tuned to do. And so in the end, what you have is you train a large language model, but you inference a whole bunch of smaller models. And those small models require a lot less energy. Let me give you one example. So we trained a large model to predict weather. And the models that it learned from are principled simulation models. And so these are, classical, physically based, principled physics simulations, and we would use those models and observed data to train a large simulation model, a large physics-based model. But when we're done, we predict weather 10,000 times less energy. Instead of using a supercomputer to predict the weather, and these supercomputers are running 24/7, trying to predict tomorrow's weather and next week's weather. Now we could use an AI model that predicts tomorrow's weather, next week's weather, 10,000 times less energy.
I think that's a point that's not widely understood, that these new weather models actually use less energy than some of the old physics-based models do. And that's had real applications in solar and wind farms, I think, and other places. And it's going to help us better understand the climate going forward.
Yeah, and that's the big idea, David. That's the big idea. I think the big idea is just to close that part of it off is the whole point about AI is not to train the model, but to inference the model. And you train the model, hopefully rarely, and you inference it, continuously. And so the amount of data centers in the future that's going to be dedicated to inference, hopefully, is 90%. And 10% is used to train the model, 90% inference models. And those 90%, we're going to save the world a ton of energy.
And say a word about how your chip design relates to that. It's more of this compute moves to inference.
Well, one of the things that's really incredible is that if you look at the way we do computation today, in the area of scientific computing, we use 64-bit floating point numbers. And the reason why we do that is because when you're doing physics, the range and the precision is sometimes hard to predict, and so the range comes from the floating point, and the precision comes from the mantissa, and so you use 64-bit floating point, and you pretty much have everything covered. You could go all the way from a centimeter down to all the way up to galactic scales, and so you cover the entire range and precision of anything that you want to do, and you never lose any precision. You never get trapped in some range, and so floating point is really good for that reason. But however, if you use AI, it has the ability to focus in or focus on the attention in the areas that you're working on. And it learns to do that. And so as a result, we don't have to use precision at 64-bit. And in fact, we're trying to always reduce the precision. And so each generation of our chip, we started with 32-bit floating point. That was our first generation AI chip. Then we went to 16-bit floating point. Then we went to 8-bit floating point. And now we're at 4-bit floating point. And so every time we reduce the precision and reduce the fidelity of the numbers, the amount of energy used is a lot less. So notice we're at 4-bit now, and so that's 8 times less energy in doing something than we were before. more than 8 times. And so now that's one way of doing it. Of course, we also have the benefit of semiconductor advances. That's slowing down, of course, but still we have, call it 20% every couple of years. We also create all kinds of new architectures so that we do computation sparsely. If you look at inside a neural network, most of the parameters are either 0 or close to 0. And so if it's 0 or close to 0, you don't have to do any math on it. And so we introduce sparsity into the neural networks. And the sparsity could, again, reduce it by a factor of, a couple of 4x or something like that. And so each generation we have all kinds of new techniques. And the goal is to, make the precision the prediction as accurate as possible, but with as little computation as possible.
You made a very interesting, innovative announcement at the GTC speech last March, and you talked about silicon photonics and how that can save energy. And my guess is many of our listeners have no clue what silicon photonics means. Could you say a word about what you announced and what that term means?
Well, we connect our chips using copper. That's the best. And copper requires very little energy to drive. The loss is quite low, but its distance, its ability to transmit information over a long distance is harder. And so we try to use copper for as long as we can. And within about a rack, one of these computing systems, we could use copper. But beyond that, we have to use optical. Now, in order to use optical, you have to convert the signal from electrical to optical. You transmit in optical, and in optical, you can go kilometers. And so these data centers are quite large. And so our chips are electrical, of course. We convert it to optical, and then we can transmit it, across a data center or even across multiple data centers. And then we have to go and convert it back from optical to electrical. Well, the conversion of electrical to another electrical transmitter to optical and back, that conversion takes a lot of energy. And so what we've done is we've created a technology that started with inventing new semiconductor process technology to new packaging technology, new SerDes technology or transceiver technologies. And we made it possible to bypass all of those transceivers and have the optical signal, the transceivers, directly connected to our chip. We call it co-packaged optics, CPO. That's the technology name. And it basically allows us to directly transmit right out of our chip optical signals. And that saves billions of dollars in a data center, megawatts and megawatts of power, and from all these transceivers. And so innovation has, it takes an enormous amount of invention to have made that possible. But now we could save data centers a lot of money, a lot of power.
As a result of these innovations, there's a lot of discussion in the energy policy community in the U.S. today about Jevons paradox, which is, I think, a term that many people were not familiar with years ago. But it's, the idea is it's a rebound effect that as technologies get more efficient, their use doesn't necessarily decline, and in some cases can even increase. And so there's a lot of people wondering, as the efficiency of AI technologies get better and better, are we going to be using less energy, or are we going to be using every bit as much energy in just generating more intelligence as a result of that? I wonder, do you have a view on that? And kind of related to that, how do you think the United States should meet our demand for energy growing out of this growth in AI?
Yeah, the answers to those two questions are exactly opposite. And so let me take the first one first. It is the case that as we drive down the cost and we drive down the energy consumption of AI, the consumption of it goes up. But you take a step back and you ask yourself, what is it that we're consuming more of or in lieu of? And so let me explain that. at the computer science level. At the fundamental computing level, what we're doing is we're moving what is retrieval-based computing to generative-based computing. And let me explain that. Most of computing today is information that was captured a priori. It was somebody, wrote a story or created an image, or maybe there's 4 versions of an ad, and depending on who you are and the context, they'll present one of the ads to you. And so these are all pre-built, pre-made content that is at the point of use, depending on its context, retrieved from storage. Okay, and so that's one example. Another example of frequent use, of course, is search. You type in some words and it come back with an index of, a list of all the different ways that you can, and then you go and click things and you go read some more, and based on what you read, you click some more other things. And every time you click something, the computer retrieves information for you. The data is, the content is stored in a storage somewhere, some flash somewhere, and some disk drive somewhere, and it's retrieved and presented to you. And so the way that computing is going to increasingly go to is that we'll retrieve a lot less and we'll generate more. And so one example is, right now while we're talking, every question you give me, I could run up to my office, pull up my laptop, go retrieve the information, and bring the information back to you for you to read yourself. That's today's computer. But instead, I just tell you what my answer is. I'm generating it on the spot. And so generative AI, in some way, you'd think it requires more energy because, my brain, consumes 35 watts. And without 35 watts, I can't generate this information at all. However, the amount of energy I saved, not running to my office, opening up my laptop, retrieving the information, bringing it back to you for you to read out loud, the amount of energy that's saved as a result of that is incredible. And so I think the net benefit of generative AI is that we're going to reduce the amount of energy consumed. The way we do search will be very different in the future. As you know, when I'm doing search, what I'm looking for is an answer. I'm not looking for a list of things for me to go read further. And so most of computing is going to move from retrieval-based to generative-based, and that's going to save energy. However, that doesn't account for the fact that all of a sudden there's a whole new way that we use computers, so new ideas come out. And so, for example, we enjoy generative AI so much that a lot of my use cases these days, I'm generating research, for example. And I do research, deep research, almost every single day now in some topic, maybe 2 or 3 topics. And I'll write up my prompt, and it could be, for example, in different ways that accelerated computing and artificial intelligence could help us reduce the energy consumption or more effectively use energy across the entire domain. And it could be from material sciences to better, more efficient energy production, like fusion reactor, plasma simulation, to wind farm simulation and better effective placement of wind farms, all the way to distribution, to power grid optimization, and predicting when power grids will go down, all the way to new ways of operating factories. And I'll just write all this stuff up, and I'll ask it to go off and do research. Now, of course, what has happened there is that this is a new use case that no computers ever had. And this new use case, of course, consumes energy. And so on the one hand, the ways that we use computers in the past will be more energy efficient. On the other hand, we're going to, because it's so efficient and so incredible, we're going to have new use cases. And so these two, I think you're going to see both of these things. Now, I'm hoping that, and we're all hoping, that the amount of new ideas for using AI in whether it's productivity applications or manufacturing or robotics applications, that we create new applications that require energy. And the net result is that the world is going to have a lot more of what I call AI factories. And these AI factories will require energy to go build. But as a result, we're going to have all kinds of new capabilities, and a new industry is going to evolve.
So as you say, these AI factories require energy and new AI applications require energy. Do you have any thoughts about how that demand for energy can be met?
Yeah. Well, one observation is that unlike the way we consume energy in the past, AI factories or AI doesn't have to go, doesn't care where it goes to school. And so you could put them further off the grid, and you could put these AI factories where there's excess energy. So that's something to keep in mind. Today, when we think about new energy consuming applications like electric vehicles, you got to park it in your house. And so it puts burden on the power grid. The fact of the matter is cell phones use an enormous amount of energy. We should apply artificial intelligence, AI, in what is called the RAN, the radio network, to improve the spectrum use, reduce the amount of energy, so that that's another way that we can improve the burden on reduce the burden on the grid. But I think the attitude about AI has completely changed. In the beginning, several years ago, the observation was that there's a new type of data center and it uses energy. And so there's a great deal of concern about that. And we're going to continue to be concerned about that and make it as efficient as possible. But the realization now is that, in fact, AI is a new industry. And this industry is about the production of artificial intelligence. You think about AI, the first thing that people think about is, of course, the capabilities of AI, what it can do. The second is the industrial aspect of it. If the demand for AI is great, then the question is, how do we go produce it, and how much energy does it require? And I think the attitude around the world now is that AI is such an incredible capability they want to bring to their country and to their industries, that you want this to be a growth industry. And you want to invest the energy so that you could have the benefit of the output of this industry. And this industry is going to have a new factory called AI Factory. The third way to think about that, and the reason why so many countries are now so enthusiastic about it, they now realize, just as water and roads were essential infrastructure, just as electricity was essential infrastructure, and the last essential infrastructure 30 years ago people didn't understand, but the information infrastructure, which is now called the internet. And of course, on top of all of that is a new infrastructure that's going to get built, and it's an intelligence infrastructure. Now, of course, the intelligence infrastructure is hard for people to understand today, but as they use ChatGPT and Gemini Pro and Perplexity and all these different AI tools and capabilities, they're starting to realize what intelligence is and what digital intelligence is and how it could be so incredibly helpful. And so now the world realized, and every country is starting to realize, that they need to have their own intelligence infrastructure. And that intelligence infrastructure is going to be built on top of AI factories, and it's going to be called AI. And so I think in a lot of different ways, companies and countries are starting to realize this is an industry they want to invest in. And so they want to go find energy to go invest in this industry and make it part of their economic growth.
What does a country need for that intelligent infrastructure? I guess it needs power. It probably needs people as well. What are the critical components there?
Well, at the core of AI, you need three things. You need of course, the data, and for a lot of countries, their intelligence is embedded and coded in the country's history and knowledge and culture, and their common sense, and a lot of it is still analog in books in their national libraries, and so a lot of that has to be has to be digitized and made available to train their own AI model. The AI technology is the second part, but that's becoming a lot more common sense, if you will. The technology, because a lot of it has been developed in open source, enormous amount of papers published in the last several years. If you look at computer science papers, it's mostly about artificial intelligence today. And so between open source models and so much publications being done in open science, state of the art technology is still rare, and in the hands of maybe a handful of companies, call it 10. But nearly every country has access to very good AI technology. And then lastly is compute. Between these three things, every country has the ability to build AI technology.
Well, there's one particular application of AI in the energy and climate world that we've been thinking some about that relates to innovation in material sciences. And I just wanted to see whether that's something that you and the team at NVIDIA have been thinking about at all. We found, for example, that you can accelerate the type of materials discovery that Thomas Edison did over the course of a year, kind of compress that into seconds probably. And that can have real benefits in energy climate change and, for example, with battery chemistry or new catalysts, lots of other things. Is that an area that you've thought about at all, and any guidance for people working on that topic?
Well, anybody who's doing material sciences absolutely must use accelerated computing and AI. There's no question about that. And the reason for that is because material sciences in a lot of ways is a lot like digital biology. You have a lot of combinations and permutations to go study, and you still must do experimentation. But if you could screen out or screen for the most effective alchemy, if you will, the most effective chemistry, then the number of experimentation you have to do is reduced dramatically. And so we're seeing enormous progress in this area to train models that understand molecular dynamics, or understand models that understand the structure of materials. And by doing so, you could essentially have a virtual laboratory, as a digital twin. And so this material sciences is one. Of course, the production of energy is another. Just smart production of energy. One of my favorite, and this is very common sense to do, and you can imagine realizing it. You need a lot of computation for it, and AI surrogate models, AI emulation is a great way of doing it. Is to design better wind farms and control the orientation of the wind farm so that you could better catch the wind and have less turbulence and generate better results. Another one that's incredible is plasma turbulence simulation in a fusion reactor. And the sooner we can create effective fusion reactors, the better for everybody. And so the list of ideas is countless. At all the way to the end, one of my favorites is digital twins. Foxconn, one of the largest electronic manufacturers in the world, of course, TSMC and Samsung, semiconductor manufacturers, they're creating digital twins with us, and so that they could plan their factory better, operate their factory better, and by doing that, you reduce the amount of energy of factories. And so you use this AI factory to create a model that simulates the digital twin of a physical factory, and the physical factory reduces its energy consumed. And these physical factories are operating 24/7 all over the world, consuming an enormous amount of energy because the manufacturing sector consumes the vast majority of the energy in the world. And so this loop of using AI to a digital twin, to an actual factory, back to the AI, into a digital twin, into an actual factory, this loop, this flywheel, is the way that all manufacturing will be done in the future.
Great. I'd like to ask about your priorities at NVIDIA, and also about one of your famous management tools called Top 5 Things. Could you talk about those?
Well, All of my priorities are in plain sight at GTC. But let me tell you about top 5 things. Top 5 things is just whatever comes to mind of your top 5 things. It could be your favorite restaurant. It could be what you're working on right now. Something you've seen recently that you consider to be really important. Maybe it's an opportunity. Maybe it's a threat. Maybe you just don't know, but it's interesting. You're curious about it. And so I encourage people to just write their top 5 things. The reason why I say top 5 things is because I don't want you to spend too much time on it, and I don't want to spend too much time reading it. And if every employee were to write top 5 things and they were all to send it to me, or send it to anybody, then we'll have if you will, edge computers, and they're sending me sensor signals, and they're over time. And I'm collecting it over time. It's affecting my brain over time, and naturally, I'll recognize patterns. And so that was the big idea when I started NVIDIA about this is 33 years ago, and instead of the other way of doing information, which is employees would write status reports to their managers, their managers would write status reports to their managers. By the time that you get the status reports through 3, 4, 5, or in some companies, 15 layers of management, by the time you get that information, there's nothing there. And so I wanted to create a system where I could afford to read almost everybody's status, but it's not too deep. It's over time. And I have to read it, you kind of read it sporadically. You don't have to send it in every week. I don't have to read it every week. It doesn't have to come from everybody every week, but it comes from everybody kind of some of the time. And so it's, so this top 5 things is basically my giant sensor system for the company. And I learn a ton from it.
Well, Jensen, you've been incredibly generous with your time, and I want to start to close up. But before I do that, is there anything kind of left unsaid on this topic of energy and climate and AI, that any points you'd like to make that we haven't covered?
I think the thing that I hope the listeners take away is that AI has 3 layers, 3 ways of thinking about AI: the capabilities of it, the industrial aspect of it, and the social infrastructural aspect of it. And there are fundamental reasons why it's so important in each one of the layers. The second big takeaway is that there's a realization that this is a new industry that's happening, and this new industry requires energy, but has measurable economic output. And so many countries are now so interested in this because many countries have excess energy, and all countries would like to have more economic output. And this new industry is really important to look at. And then third, as we think about these AI factories, and this is the area that you're going to focus on, and some of the research that you do, and I think it's really important work, is as we recognize that we want to have AI factories, we need to have AI factories. We want to build these AI factories, and it's great for the economic output of countries and industries. We still want to build it as efficiently as possible. And for the companies that build these AI factories, the efficiency of it, the performance per unit energy necessary, directly translates to revenues. And for the people who have to host these AI factories, the efficiency puts as little burden on the environment as possible. So the efficiency of these AI factories it's important to everybody involved. And so what are the best practices associated with AI factories is an area of great deep science and deep engineering. And we're doing a ton of work in that area. And so sharing best practices in this last category in the AI factories, super important. So I really appreciate the opportunity to have the conversation. And I think the net is that when it's all said and done, there's no question that artificial intelligence is the most energy efficient way of doing computation. It is the most sustainable way of doing computation going forward. And the output of this computation method, intelligence, will revolutionize so many different fields, from, as you mentioned, material science, to how we operate factories in the future to reduce energy burden on the planet.
Well, thank you for that. And so we're wrapping up our podcast with two questions for every guest. The first one is one you've actually already spoken to, which is how you use AI in your day-to-day life. And I was thinking it's kind of perhaps a funny question to ask the founder and leader of one of the world's most important AI companies. But you've already mentioned deep research and how you use that. How do you use AI in your day-to-day life?
Deep research is my favorite way of using AI. It's my tutor. The thing to remember about deep research is when you go do research and it comes back with a document, that document is static. What's amazing about an AI that does deep research, it comes back with a document. You could produce a PDF if you like, or writes a report for you. But it's not a static research. It's an active AI. This AI is now an expert in the field that it did the research on. And it can answer all kinds of questions. And so the reason why I ask it to go off to do deep research is because I want that AI to be super smart about this particular topic. Then I can interact with it on an ongoing basis. So that's one. The second is every engineer in our company is now using AI assistants to either software or design chips. And that's something that, our company is a technology company, and we wanted to apply AI in the most important area first. And so tens of thousands of engineers now, every single day, using AI assistants and helping them code. Millions of lines of code are being generated by AI in our company every day. The third area is exploring how AI is going to help us improve our supply chain. Our supply chain is super complicated. Each one of our GPUs has tens of thousands of parts. People think that our GPU is a few chips from TSMC, and it's really true that they're very important chips. But the GPU itself, the entire system itself, has tens of thousands of parts. It weighs a ton and a half per rack, and within each rack is, I guess, probably a few million parts, and from all of the different suppliers around the world. And so supply chain optimization is a combinatorial problem that's beyond any human comprehension. So we're going to use AI to try to improve on that. So these are three important areas.
Final question, speaking of the number 3, is we're asking all guests to recommend to listeners 3 books, reports, or articles that could be on any topic, old or new, classics from your childhood, something you read yesterday. Anything come to mind?
Well, when I was in my 30s, the books that were most important to me were probably Clay Christensen's collection of Innovator's Dilemma books, and really well done, really thoughtful. I miss Clay, and really impactful to our industry. And so all of Clay Christensen's books. Probably 10 years ago, I enjoyed Sapien. I thought it was really well done. Yuval Harari's book on Sapiens, I really enjoyed. Probably a history book that covers the largest span of humanity, and so that was very interesting. Lately, I've been reading books that, and now I'm kind of afraid to say it, but Chris Miller's Chip Ward book, or Graham Allison's Destined for War book, or even the Art of War book. And it's like lately it seems like all of the books end with war. And I think they're books that inform us about the tension that causes war to happen, but just a great reminder that the teachings of Art of War is about how to avoid it, and not to push the adversaries to the limit, and what you can do to either to both simultaneously compete and cooperate, so that you can keep adversaries from going to war. And so I think these it's interesting times that the nature of the books that I'm reading are changing in its nature, I guess. And but anyways, that's what I'm.
Well, Jensen Huang, those are profound and important words to end on. And thank you for all you're doing on energy and climate change problems. And thank you for joining us on the AI Energy and Climate Podcast.
Thank you, David. I really enjoyed it.